Okay, so in the class today, what we're going to talk about is this idea of the communicative property. So we have this here, so communicative. So before we do that, and just to kind of explain this, the first thing I want you to do is to have a look at these two sets. So we have the set A and the set B. What I want you to do is I want you to draw a Venn diagram for each of these guys. So 1, 2, 3, and 4. So you're going to have 4 Venn diagrams. And show me, for example, in the Venn diagrams, A union B, A intersect B, A complement B, and then B complement A in relation to these two sets here. So just pause the video and give those questions a go. Okay, so let's have a look at what the Venn diagrams will look like for these. Okay, so let's just draw 4 Venn diagrams. So we have 4 diagrams like so. And what we want to do is the first one we'll focus on is this one here. So first of all, we'll populate the Venn diagram. So if we take this one, so for the set A, okay, so the first thing I would do is look at this and look at what are the common elements. So we have 5 is common, so 5 is going to go in here. It's common between both, and maybe we should just label these as well. So this is set A, and this is set B. So 5 is common to both. Do we have any other ones? So 4 is also common. So 5 and 4, so we put them in there. And do we have any other ones? No. Okay, so then if we look at the rest of them then, so A then, for example, we have 2, the element 2, we have 3, the element 3, and 4 and 5 are common. And then for 5 then, we have, so if we 4 and 5 represented, 6 is going to go in here, and then 7 is going to go in here. Okay, so and we can do the same for the rest of these as well. Okay, so this will be A and B, A and B, A and B, and we can just replicate this. So 6, 7, 2 and 3, 2, 3, 6, 7. So 2, 3, 6, and 7, and then we have our common elements. So 5 and 4. So 5 and 4. That was bad. So 5 and 4. Okay, so we have 4 sets here. So what I want to do is I just want to color in, for example, like if we take this here, so if we take A union B, so what does that mean? So the set A union B, and we use purple here, it means both everything that's in A and everything that's in B. So you unite the two of them. So A union B, if we were to color it in, would represent everything in both of these sets. So you could represent it like so, and then you could write, for example, A union B is going to be the set 2, 3, 4, 5, 6, and 7. So that's A union B. Then if we take the set, the A intercept B, so we could represent, so let's say this, the next one, so that would be everything in here. So that's A intercept B. So A intercept B is going to be equal to the elements 4 and 5. So that's those two. The next one then is A complement B. So what that means is everything in A except what's in B. So A complement, let's use a different color, let's use red. So A complement B is going to be everything that's in the set A, but excluding anything that's in the set B. So what would that look like? So we're going to be including all of these guys here. So that would be A intercept B. So it's everything that's in A except what's in B. So I'll just write this underneath here. So A intercept, or sorry, A complement B is going to be the set of elements 2 and 3. And if we take then the last one then, so B complement A, so B complement A would look something like this. So it would be everything. So it's going to be everything that's in B but excluding what's in A. So that set would look something like this. So B complement A is going to be the set of elements, just do that one right. So set of elements 6 and 7. Okay, so that's kind of like what your Venn diagrams should kind of look like. So we want to get to this idea of what's known as commutative. So if we think in maths, for example, when we talk about, if we were to say, for example, and we've kind of come across this already, so 3 plus 4 is equal to 4 plus 3. So it doesn't matter which way you add up, like it doesn't matter which way you add. So 3 and 4, for example, is going to be equal to 4 and 3. So both are equal to 7. Now, so with addition, and also the same with multiplication. So if we have, for example, 3 multiplied by 4, that's the same as 4 multiplied by 3. So it doesn't matter which number you multiply by, which way you multiply it. Both of them are equal to each other. So both of these are going to be equal to 12. So it's said that, so that's addition, and then this is multiplication. Let's just bring this down a little bit. So this addition and this here is multiplication. Okay, so addition and multiplication, they are said to be they're said to be commutative. So we can say that these are what is known as commutatives. And what that means is it doesn't matter which way you do the operation. If you add the 3 and the 4, or if you add 4 to the 3, you're going to get the same answer. And the same with multiplication. If you multiply 3 by 4 or 4 by 3, you will get 12. So these are addition, the operations addition and multiplication are what's called commutative. Now let's just move down a little bit. Now if we take, for example, if we look at, for example, subtraction on the other hand. So let's say if we have 6 minus 2 is not equal to 2 minus 6. So these are not, so this is not, these are not equal to each other. So subtraction. So it doesn't matter which way it doesn't matter which number you subtract from the other. So if you do this first one here, so 6 minus 2, that's going to be equal to 4. And 2, that should be a 6. You know? So that should be a 6. Whereas 2 minus 6, that's going to be equal to minus 4. Okay, so these are two different values. And then if we take division then, so let's say if we look at division, so if we have, for example, if we were to say 12 divided by 6 is not equal to 6 divided by 12. So for example, 12 divided by 6 is equal to 2, whereas 6 divided by 12, I'll just get my calculator for this. So if we take 6 divided by 12, for example, that's going to be, just clear this. So 6 divided by 12, that's equal to 0.5. So we can see that these values are not equal to each other. So what we can say is that subtraction and division, those operations, are what is known as non-commutative. So they're non-commutative. And what that really means is that it does matter which way you subtract the numbers from each other, and it does matter which way you divide the numbers from each other, because the way you subtract them from each other and the way you divide them by each other will give you two completely different answers. Whereas the opposite with multiplication and addition, doesn't matter which way you add them or you multiply them, you're going to get the same answer. So that's what we mean in relation to commutative and non-commutative. Now, if we want to get back then to our sets, so what we can say then is that with sets, for example, sets also have commutative and non-commutative values. And if we have a look at this, so let's think about this. So we have, for example, so if we take A union B is equal to B union A. Oh, sorry, the wrong symbol. So B union A. Okay, so it doesn't matter which way you write this. So if you write A union B or B union A, they're equal to each other. They're going to contain, it's going to be exactly like this, either way. Okay, so it doesn't matter which way, if it's B union A or A union B, they're going to be equal to each other. The same with this here as well. So if you take, for example, A intersect B, that's going to be equal to B intersect A. So again, with this set here, it doesn't matter which way you state these two sets. Okay, so if you take A, so for example, A intersect B is equal to B intersect A. Again, doesn't matter which way you put these sets when you're using these set terminology. So what we can say then is that these two guys here, so this idea of union and intersect, okay, so this is union and this is intersect, doesn't matter which way you state it, both are equal to each other. So these are commutative. Okay, it doesn't matter which way. Like if you say this, or if you state it like this, both of them mean the same thing. And the same with this. If you state this like this, or you state it like this, if they both mean the same thing. They mean this. And these two mean the same thing. They mean this. Now, on the other hand, it does matter which way with, for example, the complement symbol here that we use. It does matter which way you arrange the letters. So, for example, A complement B is not equal to B complement A. And we could say the same down here as well. B complement A is not equal to A complement B. So again, and we can see that here. So we can see, like if we look at the sets here, we can see that they're completely different values. So if we take A complement B, we get this set of values here. and we get this. Whereas if we say B complement A, we get this set of values. So they're completely different values. So what we can say then is that these guys here are the complement. This complement terminology or symbol that we use in sets is what's known as it's non-commutative. So I'm just running out of space, so it's non-commutative. Okay, so I have to go over there a bit. So these guys are non-commutative, whereas these are commutative. So that's what we mean, this idea of the commutative property. So basically, like, so with union and intersect, it doesn't matter which way you state it, both mean the same thing. So if you put the A before the B, it doesn't matter, they mean the same thing. The same with intersect, if you put the A in front of the B, that's the same thing as saying if you put the B in front of the A. Okay, so these are what's known as commutative, whereas it does matter with this symbol, with the complement symbol, so A complement B is not equal to B complement A, so it does matter. Like if you put the A in front of the B, that's a different set than if you put the B in front of the A, like we have here, and that property holds true as well for addition. So addition and multiplication are commutative, doesn't matter which way you multiply the numbers, you get the same answer. Whereas with subtraction and division, it does matter, they're non-commutative. You'll get different answers depending on which way you subtract or divide the numbers by each other. So that's what we mean by this idea of what's known as the commutative property in relation to sets. Okay, thank you.